In this lesson, I'm going to introduce some notation to you that doesn't make much sense yet, but it will. So trust me, we're going somewhere with this. Actually, here's what we're doing. We are about to take what we've done before. Watch me as I flip through some old notes. Remember this? Exploring the area under a curve and those kinds of things. We're taking this idea and we're starting to put a little bit of calculus notation to it in a way that will make sense. So we are blending geometry, and calculus. Sing it in your head. Just make up a tune. So I am going to write some stuff down that doesn't look like it makes any sense whatsoever. Just bear with me. That is a very tall, skinny S. It is the integral symbol. This is going to be a definite integral. What is a definite integral? A definite integral is an integral, you don't even know what that is yet, but don't worry, hang tight, that has numbers on the bottom and the top. Let me just clarify that. This area goes from x values, -2 to +4, okay? So what I'm wanting to do is write this area as a definite integral, and as I do that, what I'm going to do is figure out what that function is, and don't think too hard. This function right here is just 3. Okay, so what we're really doing is finding the area of this entire thing with x values from -2 to 4, and we are dealing with moving along the x-axis. That's what we were dealing with here as we kind of looked at this and defined it. So we're going to put dx because it is the change of x as we're moving across, okay? That might look very weird to you, but this notation is going to become hugely helpful. But let's just proceed. This is equal to, and you might be looking at that saying, I don't even know what I'm looking at. Don't panic. Here's what we're doing. We're finding area. We're going to find the area. This represents that. Trust me, it'll make sense as we go through the next couple examples. All right, so this is the area from -2 to 4. Well, that is 6 units wide and 3 units high. So there are 18 square units in here. That's all we have to do. Let's keep moving. We are going to figure out the area by using a definite integral, and I'm looking at the interval as I put numbers here for my definite integral, -1 to 2. Okay, so as I did that, I was looking on the x-axis. If this graph was sideways and we're going on the y-axis or whatever, we would not put dx here, we'd put dy. We would use a different variable. This tells me a lot of things, but it tells me what variable I'm dealing with. Okay, let's put some stuff in parentheses here. Now the question is, what is this function? Well, what is this function? Well, it looks like an absolute value function to me, so we'll go ahead and do that. Absolute value, and it is shifted to the right one, so x - 1, and it is shifted up 3, and its slope is normal slope, so -1 on this side, +1 on that side. So the function is that, and we are finding the area bound between that function and the x-axis on the interval from -1 to 2. I just did a lot of pointing. Let me say all that again with the very first problem. The function is 3, just 3. We are finding the area bound between this function and the x-axis on the interval from -2 to 4. Okay? And you might say, well, why don't we just put an x instead of dx? Calculus notation, it's, oh my goodness, I wish I could go into a big lengthy explanation right now. I'm not. Here's my answer for that is not calculus based. If I just put an x here, it would look like 3x and I wouldn't know what I'm doing with it. dx is, in a sense, it's an operation. From my point of view, it is an operation. It tells me what variable I'm dealing with. Okay, let's move on. We are actually going to find this area, and you can do this all kinds of ways, and I'm going to find it using lots of little shapes. So let's do a square and 2 triangles. So square and 2 triangles. So I'm just going to write square and then little triangle and then big triangle. Abbreviate all you want. Square plus little triangle plus big triangle. And so the area of the square is 3 times 3. 3 across, 3 up. The little triangle, 1/2. 1 times 1. And big triangle is 1/2 2 times 2. Notice we're on a scale of 2 here. So when you're looking at that and you're like, oh, you really went over 2 blocks. Well, I really went over 1 unit. So 1/2 2 times 2. Okay, let's keep moving. 9 plus 1/2 plus 2. That's going to give me 11.5 square units in that. All right, things get a little bit harder. You might be thinking already, well, is this always dx? Well, for this, yes. For what we're doing on these notes at this moment, yes, because we're just getting our feet wet in it. But eventually, things will get turned sideways. It'll be dy, or we'll be doing things in a different context, and it'll be like dz or d, theta or something like that. Okay, the integral from where to where, and along what axis? It's the x-axis. -2 to 2. And then dx. So there's something here. There's an announcement. Here we go.
Please release all students that will be entering into the cultural poster contest tonight for family engagement night into Walker Commons at this time. Please release all students that will be entering their posters.
I would talk over top of her, but it's going to be kind of distracting. I hope you notice that this is a circle. This is actually a semicircle. All right, you're welcome. Okay, this is a semicircle. I'd start the video over, but I'm not. I'm too invested in this thing. So we have a semicircle right here. This semicircle is centered at 0, 0. So all this, over here I'm writing some stuff in, let's make it green so it doesn't blend in with this. Writing some stuff in here that may or may not look familiar from a previous math class. I don't have to make a poster, so I get to stay. And the radius is 2, so this is equal to 2 squared. We'll go ahead and call it 4. The center is 0, 0, so this is x minus 0 and y minus 0. So there we go. This is the formula for this circle, whole circle. I don't want the whole circle, I just want a semicircle. So I just chop it in half. Actually, let's not. Let's solve it for y, because it needs to be a function, right? So we're going to solve this for y. So I have y squared equals 4 minus x squared. And then I would square root that. And normally when I square root, I would say, sorry, that line's in the way. I would say oldest plus minus. Well, because we're dealing with the top half of the circle, we're going to keep the positive one. So here's what goes in here. Here's what just happened. I found what the function was. I found what the function was. It was 3. I found what the function was. It was absolute value. Shifted 1 to the right and up 3. I found what the function was. Oh, it was a circle and I had to figure out the top half. That's what it is. And it is 4 minus x squared. Okay, so let's just think about some geometry that we can use on this. I'm dealing with a semicircle. So half of a circle would be, well, pi r squared, but I just lied to you. It's actually 1/2 pi r squared because it's a semicircle. So 1/2 pi times 2 squared, which is going to give me 4. Then half of that would be 2. So 2 pi square units. We don't know what the units are, so we won't do it. Okay, sliding up, going a little faster now. From where to where? There to there. That's -3 to 6 along the x-axis. What is the equation? It looks like a line to me. Don't make it harder than it is. Y equals mx plus b. So my slope is 1/3. Yes, it is. 1/3 x plus 2 is my y-intercept. That is the setup. This is the definite integral that represents that. If someone handed you this and said, represent that on the coordinate plane, you'd graph that function. You would color everything under this line between -3 and 6 on the x-axis, and it would look like this. Just saying. Just saying. Okay, we're going to figure out what the area of this is. We have a couple options. We could split it into a rectangle, see that rectangle, and a triangle, or we could just do a trapezoid. We've done trapezoids very recently, so let's deal with the area of a trapezoid. So I'm just going to write the word trapezoid here. And so we'll do 1/2 height, base 1 plus base 2. Okay, height is not always height. Like, notice where my fingers are going. It's not like height, 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 height. No, it's, in this case, it's height, which would be 9. And the length of the two bases are here. That would be a unit of 1. And here, which is 4. And we'll figure this out, hopefully without a calculator. That would be 4.5 times 5, and that's going to give me 20 plus 2.5, so 22.5 square units. All right, moving on. Things are going to get a little tricky now. Here we go. From where to where? -3 to 4. Good call. What's your function? It's this line. What is this line? Slope of 1, y-intercept of 0. It's just x. dx. That's it. Okay? Again, the reason we use dx, big long list of reasons, but for me, it makes sense that we wouldn't just use x, otherwise we'd have x, and you'd be like, oh, it's x squared. No, that'd be crazy. Let's not. dx tells me which axis I'm going along. All right, let's figure it out. We have a little triangle and a big triangle, so I'm going to write that. So little triangle, and then plus big triangle. Someone's knocking on my door.
Hey, I have a student for you.
Come on.
Okay?
Yeah, not a problem. Send him in.
Kevin, you can just sit in here silently.
So we're going to find the area of this little triangle. And when we do, we are going to just look across here. We're going to have 1/2, 3. And now this is where things get tricky. 1/2 base is 3. And the height, you might say, well, the height is 3. And I hear you, but we're actually not going to talk about height so much as we're going to talk about the value of the function. Okay, so like here when I said, oh, it's 1. Well, what is it? It is 1. The value of the function was 1. The value of the function was 4. The value of the function is -3. Okay, that is, in a minute, that's going to result in a negative area. I know that sounds like a wacky thing, but computationally it works. All right, here goes. Big triangle is going to be 1/2 4 times 4. 1/2 4 times 4, so 1/2 3 times -3. That's going to give me, well, half of 9, so -4.5. And 1/2 4 times 4, that's going to give me 8. And I end up with 3.5. Now, if you're looking at this and saying, that's more than 3.5 square units, of course it is. Absolutely is, because I have both of these to count. But because this one was, for our purposes at this moment, I'll say it this way, things can change later, but because this one is below the x-axis, we're going to count it as negative. In a practical sense, it may not make sense to have a negative area, but from a computational point of view, I had to use a -3 for my height. Okay? Alrighty, on the back side, and mine's on a separate piece of paper, on the back side we get some craziness going on. So I'm flipping this over, and I want you to notice what's happening on this one. In case you really want to know about this one exactly and what the actual function is, I'll go ahead and tell you. Well, let's go ahead and do this. -pi to pi. And the function itself is this little guy right here. And that function to me looks like, well, sine. How do you know? Well, because I'm telling you. But here's another reason you know. It goes up to 1, goes down to -1, goes from -pi to +pi. It just looks like sine, smells like sine, it's sine. And we're going along the x-axis. So at this point, if you're panicking and you're like, well, what shape would I use? Is it a semicircle? No, it's not an exact semicircle. Well, is it this or is it that? Do I break it up into triangles or rectangles? No, you don't. Can I go ahead and tell you the answer? I think I will. Here we go. This and this are equal in area. I have no idea what this is. I have no idea what this is. Actually, I think I do, but I'm not going to tell. But if I don't know what this is and I don't know what this is, I might seem lost, but here's the fun part. That is negative whatever, and that is positive whatever, and they will cancel each other out. And I am left with 0. That's it. Okay. Next problem. You might look at that and say, whoa, things are getting a little bit wacky here. I agree. But let's just go ahead and write. Check this out. It's going to be fun. We're going to write this in pieces. It's totally okay to do this. We're going to find the area from -5 to -1. Why'd you stop there? Doesn't it go to 5? I hear you, but look, it's broken into pieces. So let's break this into pieces. -5 to -1 of this equation along the x-axis. And this equation has a slope of -1. And if you extended it, you'd cross the y-axis at 0. So this line is actually just -x. Okay, we'll take care of that one in just a minute. And we're going to find the area here from -1 to +1, -1 to +1. And let's figure out what that equation is, but it is, of course, along the x-axis. We'll deal with that one in just a second. And let's just move on. From 1 to 5, this horizontal line is 2, and we're going along the x-axis there. The only thing we haven't filled in is that. So let's just jump over there and do that real quick. Green pen. I'm going to try to squeeze my work in down here if I can. This is a circle that is centered at 0, 2. So x squared plus y minus 2 squared equals 1 squared. And we're going to move everything over to one side except the y. We're going to solve for y, basically. So we're going to have 1 minus x squared. That would equal all this stuff, which is squared. We will square root that, and then we would have to add the 2. We have now solved for y. I did a lot of work because I had very little space. A lot of work in my head there, but subtract x squared, square root, add 2, that's it. And that's going to go right here. We'll write it in green just to make it nice and pretty. 1 minus x squared and then plus 2. Add to the square root of 1 minus x squared. Okay. So now we have to figure out this area. Oh no, what are we going to do? We're going to panic. This area right here looks to me like a trapezoid. This area, break it up into pieces if you have to. It's a semicircle and a square. This is a rectangle. This one and this one are going to be easy. This one takes a little bit of work. Let's move on. This trapezoid right here is 1/2. Height is 4. And then we're going to go from 5 to 1. Or 5 plus 1, I should say. The base is 5. The other base is 1. Those are the function values. This one is going to have a positive area. Notice the whole thing's above the x-axis. All right, next one. We're going to break this up into 2 pieces. One of them is going to be the square, so the little square, which is 2 by 2. I'm going to write 2 times 2, even though we all know what that is. And we also have a semicircle, so 1/2 pi times my radius squared, and my radius is 1. And then we have this little, finish that. Then we have this little rectangle going on, which is 4 by 2. Okay, let's do this without a calculator, he said as he was looking at his calculator. 2, I'm not. See, it's not even on. 2 times 6 is going to give me 12, plus 4, plus something with a pi in it. We'll call it pi over 2, plus 8, and like term, like term, like term. That one's not. We'll just put him first because he looks special. And 24. Pi over 2 plus 24 square units. Yes. Okay, one more. And I just want to point out what's happening here. I think it's fairly obvious on this one that we have a vertical asymptote. And this vertical asymptote is going to create somewhat of a problem because I don't know how much area there is because it goes up forever and ever and ever and ever and ever and ever. And so is this an infinite amount of area or a finite amount of area? I wanted to throw this one in here to talk about continuity, which is going to be part of a conversation in just a minute, and how it relates to whether or not I can do an integral, which is integrability. In the meantime, let's just set it up. I told you what the function was. That doesn't look like the integral symbol that we're used to. 0 to 10, remind me to tell you, you can't do that on a video. Remind me to tell you where this symbol comes from. X minus 3 squared and then plus 2. There we go, that's it. And the final answer, you want to know? I'm glad you want to know because I'm going to tell you. The final answer is undefined. Or you could say infinity. You could say it does not exist. It's basically an infinite area. I'm going to write it that way. Infinite area. Are they all like that? No, they're not. This is a Calculus BC topic. So eventually we will tackle problems like this where we actually try to find that area. But I have worked through this problem. This one is indeed an infinite area. It gets really crazy really fast. It's kind of fun. Okay, let's have a conversation about whether or not I can take an integral, whether the function is continuous or not. So every single one of the problems on the front was continuous, 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 continuous. And this one was continuous. I could find the integral of all those. Continuous, no, not continuous, but I still could find the integral. Not continuous, but I couldn't, and I wasn't going to work through the work right now. Again, that's above our pay grade at this point. So let's make a statement about integrability and continuity. We'll write it down here in this great big box. If a function, which we will call f, and it is continuous on an interval from a to b, then f is, okay, new word, and you can see it right here. F is integrable on same interval. So if I have a function that's continuous, then I can integrate. What does integrate mean? Well, glad you asked. Integrate means I can do this, and I can say that that exists. Another way of wording it is I can find the area. I can find, or at least approximate, the area. Okay, so if a function is continuous, then I can find the area. If a function's not continuous, I, look where I'm pointing, may or may not be able to find the area. All right, I'm gonna write a couple other things over here on the side because we've talked about continuity, integrability, differentiability, all those kinds of things. So a couple other random thoughts that are somewhat related to all those ideas. Continuity implies integrability, which is actually what we just wrote here, but this is an abbreviated version. Integrability, that's one of them. And then here's another one. Differentiability, the ability to take a derivative, differentiability, yes, implies continuity. Okay, every differentiable function is continuous. Every continuous function is integrable. Not every continuous function is differentiable. Not every integrable function is continuous. Whew, that was wordy.